No?
It's gonna come in on a chariot of fire.
Well, that'd be appropriate, actually, given the topic.
I think he just went to get you, and so it's like playing catch up. But there you go.
I think we're all here finally. Oh, amazing. Well, it's my pleasure to be able to introduce Matt Marshall to you. You all know Matt. And so I'll just give you a little bit of a background. He went to, grew up in upstate New York, went to a small college in upstate New York. If I get it right, St. John's Fisher College?
Yep.
Yeah, and he was the athletic guy there. Actually in high school too. I think he played just about every sport that I know of.
Everything but baseball.
Everything but baseball. Okay. And so anyway, he went on to college, and somewhere in his journey decided that there was something more intellectually challenging than football or rugby or whatever. And so he came down here, got his master's degree with Matina several years ago, and then decided to make a switch and wanted to work on an increasingly hot topic. So today he's going to give us a presentation of his dissertation proposal.
Thank you, Elizabeth. And thank you all for coming to my dissertation proposal. Today I'll be discussing the genetics of thermally sensitive phenotypic plasticity in Plantago lanceolata. So here's an outline of my talk. First I'll discuss a pressing environmental problem, followed by my research questions. And the reason that I chose Plantago lanceolata as my study species to address these questions. Then I'll get into my two different studies, first an AFLP study, and then an experimental crossing study, followed by the broader impacts of my research. So, I know you're all well aware of climate warming, and we know that Earth's climate's been changing since forever. However, the issue is not just that the temperature is increasing on the land and atmosphere, but that it's increasing at this exponential rate. Many people are concerned that the rate of climate change may threaten the existence of many organisms because this may be happening too quickly for many species to adapt. And additionally, as the Earth continues warming, it is expected to continue warming at an accelerating rate. So as these climate zones warm, they will shift faster. Animals most at risk are those that are long-lived, such as these large mammals shown here. And that's because they take a long time to go through generations. Adaptive phenotypic change is one way that may allow organisms to survive in a changing climate. And phenotypic plasticity is an individual response to the environment, and therefore happens quickly compared to adaptation because it happens within the lifetime of an individual. In this example, I'm showing thermally sensitive body size of Drosophila, in which individuals grown under cooler temperatures have a larger body size than individuals grown under warmer temperatures. So to measure phenotypic plasticity, we can calculate it two ways. One is the difference between these phenotypes. So this body size minus this body size would be the measure of body size plasticity in those two thermal environments. Or we can measure it as the slope of the reaction norm, or the line that connects those two dots on a graph. Because thermally sensitive plasticity can allow individuals to adjust their thermal tolerance, and therefore it promotes survival in variable thermal environments, under our projected climate change model, thermal plasticity may be very important for organisms to survive in that changed environment and then be able to adapt. As you all know, temperature has a very strong influence on your performance. Some of you were too cold when you came in here and you figured you might not be able to pay attention as well. But also when you're too hot, you can lose performance as well. And so I'll illustrate this graphically on a thermal performance curve. At your optimal body temperature, you perform the best. And as your body temperature veers, either decreases or increases, performance drops off until it reaches zero at some critical maximum or critical minimum. By responding phenotypically to the environment, some organisms are able to shift this thermal performance curve. So when the external temperature that was here increases, by shifting their thermal performance curve, many organisms can maintain high performance at a new body temperature. Thermoregulation can allow organisms to regulate their body temperature and decouple it from the environmental temperature. So under this scenario, with the external temperature here, we would expect performance to be decreased. However, if this organism can thermoregulate, it can decouple its body temperature, cooling it down, having a cooler body temperature than the external environment, and maintaining higher performance. There are many different mechanisms that this can occur by, one of which is physiology. And this is an example of a bat that Rada and I found in an old abandoned mine one time. And in that old abandoned mine environment, it was much cooler than the outdoor summer air. So this bat goes in there to sleep, and it can reduce its metabolism and body temperature to decrease the difference between its internal body temperature and that cooler cave-like environment. This is a picture of a vulture that I found one morning, and it had its wings spread wide open towards the rising sun to absorb that thermal radiation and warm up that morning. Oftentimes, the environment varies in its thermal properties, and organisms can move throughout the environment to maintain a body temperature near their optimal. Most of you don't really think plants move that much, however, they just move a little bit slower than animals. And so this is some time-lapse photography sped up about 1,000 times. And it's an example of a water lily that the flower opens when the morning sun hits that flower. These flowers then track the sun throughout the day, and in the late afternoon when the sunlight fades, they close their flowers up until the next morning. Then the sun rises again, the flowers open, and they close again that afternoon. Morphology is another mechanism by which organisms can regulate their body temperature. This is because body size and shape have a strong influence, they directly influence the surface area to volume ratio. Bergmann's rule, established in the 1800s, observed that in endotherms, it was often seen that they're larger in cool, high-latitude environments. That's because these individuals found in the north having a larger body size also have a smaller surface area to volume ratio, and therefore they dissipate heat more slowly than their small counterparts. Allen's rule, along the same line, suggests that endotherms should have shorter limbs in cool, high-latitude environments, because shorter limbs produce a more rounded body and therefore smaller surface area to volume ratio. In environments where it may be adaptive to dissipate more body heat, long limbs are often found. In ectotherms, there's the temperature size rule, in which oftentimes ectotherms are larger in cool, high-latitude environments. So as the environmental temperature in which Drosophila develops decreases, they form larger body sizes. And many ectotherms follow this pattern. So just a brief summary of what I've covered so far. We know that Earth's climate's been changing on a millions of years scale. However, it's remained relatively stable for the last 10,000 years or so. Today, due to human activities, we see this exponential increase in temperature that's happening very rapidly. And thermoplasticity may be a mechanism by which individuals can respond to this temperature change and adjust their thermal tolerance. However, today the genetic basis of thermoplasticity remains poorly understood. And this is a problem because a major goal of biologists is to forecast and mitigate the effects of climate change. By understanding the genetics of thermoplasticity, we will be able to evaluate how selection has acted on plasticity in the past and evaluate which environments plasticity may be adaptive in, as well as better predict the future response of plasticity to selection. So for example, what trajectory would plasticity